Are there any questions before I start from lecture 22? 21, sorry, this is lecture 22. Yeah, I'll review things. So if there are any questions when I review, please ask. One important comment, hopefully everybody hears this. I'll post it on Brightspace as well if I remember. November 12th, which is next Tuesday, and November 26th, which is the Tuesday of Thanksgiving week, we're going to be on Zoom. Unfortunately, I'm out of the country for those days. All right. That is, those are the only comments I had for now. Shall we start? Okay. So review of lecture 21. What we talked about in the previous lecture was we talked about rotations and how even in classical world, they do not commute. If I rotate this table in this direction, followed by this rotation around this direction, I get a different result if I do them in a different order, right? And then we said every time we talk about actions in physics, in our theory space, whatever it is classical world or quantum world, what you need is a representation of your action in terms of a matrix, right? So if I'm thinking classical physics, a bunch of vectors, this table is like has three-dimensional positions, and representation I'm picking to describe this is three-dimensional real vectors, right? So that's a representation. Now, if you're talking about the Hilbert space, you will have to pick a representation of the same operation in the Hilbert space, and we're going to see that there will be there would be unitary matrices, which are complex D by D matrices, where D is the dimensionality of the Hilbert space, right? All right. Of course, they will not commute. It doesn't make any. The representation has to maintain the commutation relations, right? Okay, so in the we discussed this in length last time. If in the three-dimensional vector language, a rotation, you could think of it as a matrix acting on a vector that keeps the length of all vectors invariant, right? So the way to see that is, well, that condition means that R transpose times R is equal to R transpose equal to identity. Such matrices are called orthogonal matrices, but I'll describe a little bit more, right? So by the end of the lecture, we'll talk a little bit more about that. Is it clear where this comes from? Or should I do it on the board? So we did this last time, right? What's the length of a vector? This is x, y, z. This is the length squared. This is the length of a vector. So if I have v, I can think of this. This is my vector v. This is v transpose dot v is the length of the vector squared. All right. So if I'm applying a rotation here, this is my rotation matrix, right? Now, of course, if I rotate the matrix and if I rotate the vector and the length of it doesn't change, it means that I have to rotate this and I have to rotate this guy as well. But this is what is the result? So let me just write here. So this is RV dot RV transpose. This is V transpose, which is this R transpose. Right? Transpose is just like switch the rows and columns. This has to be equal to V dot V. V transpose dot V, right? Which is this. That the only way to do that is R transpose times R has to be identical, right? For all such matrices. And of course the reverse order as well. Good. That means that R transpose is undoes the rotation. Right? The inverse operation is R transpose. All right, so these are orthogonal matrices. We're gonna take, given an orthogonal matrix, we're gonna represent it on the Hilbert space in some notation that I'm calling curly D of R. I think that's the notation of the book. That's the general, very mathy notation. So this D of R acting on some D-dimensional Hilbert space is a D. This is a D by D complex matrix, right? Why complex matrix? Because the Hilbert space is a complex D-dimensional vector space. All right. Analogously, we'll see this. That can you so this relation is going to be replaced by D of R dr dagger equal D of R dagger D of R equal identity. This is what defines a unitary matrix. Unitary matrix, right? Why can you fill in between this argument and this argument? What is this condition? Norm. So for complex vectors, we said the notion of length is replaced by norm, right? And this is a condition that the norm of the vector should remain preserved under rotation, right? That's reasonable. That's sensible. We'll come back to this. All right. Any questions so far? So how are we going to go about constructing these matrices? Well, we already sort of hinted at this, and you can see a theme in this course, which is a sort of a systematic way of constructing these transformations, starting from well, okay, so we did the same thing for our space and time translation. So if this is your unitary transformation for an infinitesimal amount of transformation, doesn't matter what transformation it is, as long as it's like a unitary thing that represents, it has to be grouped, but we'll see that. So this is the unitary, so you can write it as identity minus IG epsilon. Why is there an identity here? Every transformation, whether it's translation or rotation, has a variable. How much did you rotate or translate it with? And if you pick that variable to be 0, it should be represented by identity. A rotation by amount 0 or translation by amount 0 is nothing, should do nothing to your vector, so that's identity. Hence this. Then if you linearize it, the coefficient of epsilon, you could write it as IG. Why do we pull out the I? So that the generator is self-adjoint. Right? We worked this on the chalkboard, that the requirement that you as a unitary tells you that this guy, you have to pull out an I so that this is the infinitesimal generator is self-adjoint or Hermitian. I keep saying self-adjoint because I'm anyway. Then for the case of translation in space, we said that we argued just based on general grounds that this has to be momentum operator, which is the generator translation, divided by h bar. There had to be an h bar there just by dimensional analysis. And then here, this epsilon, small amount of translation is just dx prime, right? Like a little bit of a translation. We did the same thing for time translations, and the generator of that is Hamiltonian. And the infinitesimal generator is just tiny amount of time translation. For rotations, what we can do is, well, we do the same thing. Epsilon is just d phi, an infinitesimal rotation, and the generator here is going to be some operator j hat k over h bar. So we're going to describe this. We did describe this very quickly, briefly, but we're going to beat this up and discuss this in detail, right? But you see some sort of a principle. It's as if like if I want to talk about quantum mechanics, the starting point is symmetries. Pretty much in all analyses in physics, most analyses in physics, the starting point is symmetries. You identify the symmetries of the system. And importantly, this h bar is the same h bar in all of these. We argued for that here. Actually, by the end of this lecture, you will have an example to argue that this h bar must be this h bar. But I'll leave it to you to figure out. All right. So more generally, if you're talking about a finite rotation around some vector n hat, some direction, some ray n hat, by angle phi, or sorry, infinitesimal angle d phi, this is an infinitesimal rotation, we can write it as identity minus this one is identity, okay? J dot n hat over h bar d of phi. I will explain this through many examples today, over and over again, but I want you to remember this, and I'll come back and comment on this. This is the general form of it. It's just, like a generalization or another repetition of the same idea, right? Because rotations, so here you could have said that instead of talking about translation in space, we just talked about translations, space or time, right? And then the generator would have carried a label K, that would be the momentum in space, or if that label is 0 or time, it would be Hamiltonian, right? So similarly, rotations, there are a few of them, right? There are a few independent rotations. How many of them are there in 3 dimensions? How many different angles do we have for rotation in 3 dimensions? 3, yeah, exactly. So that's why this is a vector worth of things. All right. We do not want to comment on that. All right. Now, I want to highlight this because I think I absolutely recommend learning this idea. Whether we're talking about translations or rotations, you see the following structure for your matrices. There's always an identity. This is doing nothing. And identity, the defining property of it is that if you do some transformation followed by identity, that's like just that transformation. Identity doesn't do anything. So the first line. Then closure. If you rotate and rotate again, the net result is a rotation, right? So same for translations. There's an inverse. If you rotate, there's another element of the in your set of transformation that will undo it, right? And then associativity, which is the fact that even though the order could matter, but those parentheses don't mean anything. So you just do 1, 2, 3, right? Any transformation with such properties is called a group. This is an incredibly powerful idea from mathematics, and the realization of the role of group theory or groups in physics really revolutionized 20th century physics. It really essentially taught us how to properly think about quantum mechanics. All right? So abstractly, all these transformations you're talking about are well, not all these transformations. The transformations we're talking about, translations in space and time, and rotations, are groups. Now, 3 by 3 matrices are a representation of it. A representation is a way of representing the transformation by matrices. This is it's a real 3-dimensional representation. Right? Makes sense? You're representing it by 3 by 3 real matrices. When you go to the Hilbert space, the representation, whatever the hell it may be, must satisfy the same properties, right? And now that D of R, depending on what Hilbert space it acts on, right, it would be a different set of matrices, right? For example, we're going to discuss this. If you're acting on a 2-dimensional qubit Hilbert space, D of R is going to be a 2 by 2 complex matrix, right? Good. So even though you never thought of it in this language, in classical physics, you're already using representations. Any physical theory is representation theory, but that's an abstract concept. All right. We talked about the computational relations of the generators. So we took some, so now that we have this master formula, what we're gonna do is we're gonna just expand the commutators. Ooh, what am I doing? Yeah. To the second order, and expand the unitaries to the second order, and then calculate the commutator. We learn from it that the generators must satisfy this commutational relation. More generally, you could abstractly write this out. These are Jx, Jy, Jz. So Jy does what exactly? It generates rotations in the Hilbert space around axis Y. So in the Zx plane, right? That is what it is. And this is the totally antisymmetric answer. Notice this I. When you're talking about real matrices, the commutator of on this side, there will be never an I, right? But here, the I is, you could convince yourself there must always be an I if you're talking about unitary representations. Good? Any questions? the rest of this lecture, and actually probably the next lecture, is explaining all this abstraction in examples in more detail, right? So we'll come back to this many, many times. But hopefully, I guess I try to give a high level presentation first, and then we'll go through it, okay? But if there are any questions or concerns, ask now. Yeah.
So I think earlier in the course, we saw that under certain approximations, representation of the system for just classical mechanics, right? So do these 2x2 complex matrices yield like just a 3x3 real matrix?
We'll discuss this in detail. That's the case of spinors.
Oh, okay.
We're gonna see how spinors come about. So you might have asked yourself, what the hell is a spin, right? Hopefully we'll explain that. Well, we'll not explain it absolutely systematically, but you'll have some bedtime story to tell yourself when spinors come, where spinors come from, right? In this course. But if you're taking the QFT perspective, which is like very, very symmetry comes to the center of the picture, then it'll be very fun, like principal derivation. All right. So what am I gonna do for now? I'm going to talk about pick a quantum system that is a qubit, two-dimensional complex vector space, right? And then talk about representation of rotation group on this three-dimensional space rotation group and the two-dimensional complex vector space of qubits, right? Hopefully by now you have seen all the math behind it. These are things that we started this course with, right? We talked about the silver atoms, these rotations. Maybe it would look like you pull this out of the box. It seemed a little bit random at the beginning. It was very, at the beginning, it was very like experiment motivated. That's what we were making some observations. Now we're explaining it in more fundamental, rigorous sense, well, theoretical sense. All right. So what was our SX operator? So what is SX? SX was h bar over 2, 1, 1. It's an observable. SX is the generator of rotations that fixes the x axis. So it generates rotations in the y-z plane. And this is this representation in the two-dimensional complex vector space, right? SZ similarly is this, and SY is similarly this. Now you sort of see why there was an I here. Well, maybe you don't see it, but actually, can you see why there's an I? Why is there an I? What are you trying to represent? You're trying to represent three different rotations. So you need at least three independent things, right? With 2x2 matrices and real components, this is all you've got, right? So there's an I sneaking up. You might ask, why is there no fourth one? We'll get there. All right, but the counting works. All right, so the representation of a rotation, let me write it on the board. So rotation around the z-axis by what they call it angle phi is this cosine phi minus sine phi. I think minus sine phi is the notation of this book. Cosine phi flat. All right, this is my notation, and this is a special case of something that I usually call R n phi, rotation fixing the n hat vector by angle phi. Right, so this is the hat. Please understand. What is this? Oh, I voted. All right. Good. So what is a representation? This is the Hilbert space. It will be some matrix, 2x2 complex matrix that I can write in different ways. That's your choice of notation. Let me write it suggestively this way. So R of Z of phi, right? So this matrix is now represented in the two-dimensional Hilbert space as exp exponential of minus sz, right? dot, oh, sorry, there's no dot. Good. It's convenient to define these Pauli matrices in case we had it. I think we had, but sigma 1, sigma 2, sigma 3. By now, you've seen pretty much all the most important symmetries of nature. Rotation, except for one, but you already sort of know it. Translations, rotations. What else is there out there? There's one other fundamental generator that we haven't discussed. It won't be relevant for this course, but sorry? Reflections are, that's a very good one. I did not mention that. Those are very good. Those are discrete. So I'm talking continuous transformations. Time translation we talked about. So boost, right? Special relativity. What is boost? In boost is rotation between time and space. That's literally what it is. Like mathematically, it's identical. That's how initially Minkowski realized that Einstein's, it's elegant to think of the space-time as time as a dimension. The reason is that boost mathematically is like rotation in space-time. That mixes space and time, right? In the rotation is in some XY plane, say, and then if you have a rotation in XT plane, roughly speaking, if you keep track of everything properly, that's boost. So mathematically, you've seen all aspects of it. Modulo some subtleties that you could learn if you want to go down that path. All right, that's why, as a matter of fact, even in relativity, quantum field theory, these matrices again play an important role. Right? So Pauli matrices. A bunch of identities that they satisfy. These are very, very crucial. A Pauli, so you'll remember this, right? I don't need to write it on the board. Let me write it. Always forget to drink the chocolate. So these are Pauli matrices. First of all, they're all Hermitian. They're observables. So they're equal to their daggers, right? Property number two, this is very special to them. They all score to identity, right? Just multiply them by themselves. Property number three, if you take a pair and multiply them, sigma 1, sigma 2, and symmetrize this, plus sigma 2, sigma 1, you get 0. Right? So just do the sigma 1, sigma 2 is minus sigma 2, sigma 1. It's just a fact about the matrices. So you can elegantly write that in the language of the anti-commutator. Hopefully, do you remember anti-commutator? Let me just write the definition for future reference. Oh, oops. So the anti-commutator is AB plus BA, right? But it's just like an elegant way of writing this property. I'm listing properties, right? Like I'm not, then the commutation relations are these epsilon JK thing that we discussed, right? They are all traceless, right? Just it's a fact. Take the trace of them, it's 0. And they all have determinant -1. Good. All right, there are 3 of them. And if you want to represent a rotation, there are also 3 angles, right? So it's convenient to define this beast, sigma, which is a vector. This is some sort of a convenient but complicated notation. Yeah, I've written it, but so when you write sigma, now how do I want to write it? Okay, I write it this way. A, right? This dot is something that we never talk about really. This is just compact notation for sigma 1, A1 plus sigma 2, A2 plus sigma 3, A3, right? We saw this in the homework without explaining it, and there were good complaints, reasonable complaints. I should have put this on my something. Okay. All right, so when you multiply these guys, this is just notation for this guy, right? A 2x2 matrix, which is A3 minus A3, A1 minus IA2, A1 plus IA2. Good. Of course, it's an observable, meaning there's Hermitian. Of course, it's traceless. Good. Trick question. No, never mind. There are no tricks in physics. Right. So now what we're gonna do is we're gonna come up with a representation that has to do with rotation around the vector n hat by angle phi. So that representation is going to be exponential of minus I s dot n. Okay, so remember what s's were: si, sx, sy, sz, s1, s2, s3, however you want to call it. It's h bar over 2 sigma L matrices, right? Remember that? That was in the previous slide. So my h bar is weird looking. Oops. This is the representation of rotation on around vector n by angle phi. Why do I put a hat here? So this hat is ultra confusing notation. This is not an operator, right? It just means unit vector. But why do I not care about the length of the vector? A rotation that fixes some axis doesn't matter how you label that axis, right? It's just n hat, some vector in that direction, right? Now you notice, oh, I'm so sorry, there are just too many n's here. Let me change notation. An interesting property is that if you take this guy, sigma dot n, and take it to some even power, you get 1. It's just a fact. Multiply them and see. And if you take them, I'll put this in as a homework problem. And if, of course, if you take it to an odd power, you get sigma dot n. This follows from that one, hopefully. That's right. Do this as a, well, I'm tempted to do a homework problem. All right. Any questions? These are just algebraic relations that, yeah. Should S be oh, did I mess this up? Yeah, I think I changed the notation. Oh my God. That is bad. Yeah, so let me how do I want to do this? Well, this is what I want to have, right? Let me see, how do I have to define things? Very good. Yep, sorry, thank you. That was important. That was an important typo. I want to have this over h bar and this should be over 2. Thank you. Sorry about that. Right, that makes sense because S is h bar over 2 as the root over here. So h bars cancel and you get 1 over 2 down. That 1 over 2, just 1 second. That 1 over 2 is the reason we have fermions in nature. That's the reason we have spinors. This 1 over 2, that innocent looking thing, is placed. That's literally the reason. We'll see that by the end of this lecture. So thanks for the correction. Any questions? There was a question. Yeah.
This rotation is like spin. So what is it doing in the context of this?
Okay. In nature, there are all sorts of particles, and for now, let's pick, and they come with a property, quantum mechanical property called spin. Let's pick a particle that's spin half. We said that should be modeled by two-dimensional complex vector space. If what this tells you is that how rotation acts on that particle. So rotation acts differently on different particles. And if your particle has spin half, this is how it acts on it. When you say, yeah, is that
You said you started with some particle spin, you want to rotate it, you can model it like that.
yeah, like literally, we had this example, the Stern-Gerlach, right? You had spin half silver atoms, so you were measuring something. Whatever that measurement was, let's call that, I don't know, SC. Then you took your device, apparatus, and rotated it. And then this is what you did to your kets and operations, right? There's something very weird going on. Can you tell what that well, maybe at this point it's hard to see, but that half has dramatic consequences in physics. All right. Any other questions? Thanks for correcting that type, but that was pretty bad. By the way, I think it's an unfortunate thing about the text. I dislike that fact about the text, that there are several different notations. And I'm following the notation of the text, but S is the same thing as I've been calling, well, it's spin, right? So I'm using S, J, sort of, I go back and forth. There's a historical reason for that. And yeah, if you see S's and J's, sometimes there's a reason behind that, but like they're basically representing the same concept, right? Any questions? All right, so why did I say these identities? The reason I said that I mentioned these identities is that, well, this is an exponential, so Baker-Hausdorff, no, not Baker-Hausdorff-Campbell, expansion of the exponential, right? Just Taylor expansion of the exponential. What do you get? Just take this. You get various powers of this, right? Well, you know what you get, right? Let me just write that down. Minus I over 2 phi to the power of n sigma dot, well, let me call it m. This is the expansion of an exponential, right? So let's package, because we said that all the even powers are 1 and all the odd powers are sigma n. So let's pack together all the even powers and all the odd powers, right? So you get these two lines. Once you sum them up, you realize that this is the Taylor expansion of cosine, and this is the Taylor expansion of sine. Not surprisingly, right? Because xp of I phi is sine phi plus cosine phi plus I phi, right? So written in the language of 2x2 complex matrices, this is what the operation of rotating around the n-axis by angle phi is. This is the answer to your question, right? Like I had a apparatus that was measuring SZ, and then some kets were coming in. Now I say somebody comes to some graduate student comes to the lab and said picks a random n-axis and rotates the device around the n-axis by angle phi. How does that change your kets? By the action of this matrix, right? Yeah. What makes it clear that this specifically for spin half? 2x2 matrices, because we modeled spin half by two-dimensional complex vector space. In a sense, the spin is telling you about the dimensionality of the Hilbert space. We'll see that. I said that last time in passing. Spin J particles will have Hilbert spaces of dimension 2J plus 1. So spin half would be two-dimensional complex vector space. What would be spin 1? 2J plus 1. All right. Okay, That's 3. But notice this half. So I'm gonna make a big deal out of this half because it's an important thing. Notice that these are 5 halves, right? So an interesting calculation you could do is actually, let me move this down here. Is the following. For a second, ignore down here, what I've written down here. So we're just gonna focus here. So an interesting thing about this is that if you put in 2 pi, you get sine pi and cosine pi. Right? What is sine pi? 0. What's cosine pi? -1. So rotation around axis n by 2 pi, you do not come back. Your ket does not come back to the initial ket. It picks up a minus sign. Remember when I was talking about fermions, I said you rotate them by 2 pi, you pick a minus sign? This is what that is. Is this minus sign observable? Let's vote. Is this minus sign observable? Who says it is observable? Oh, you guys can be more brave. All right, doesn't matter. I'm not gonna poll. This is early in the morning. Okay. The answer is yes, but it's subtle. If you took the whole world, right, and rotated everything around an angle, right, then a minus sign multiplying all kets won't change anything. Why? This minus sign is a phase. The overall phase of all kets in the universe doesn't have a meaning. The only thing that has a meaning is that if you have 2 particles of spin half, you rotate one of them by some angle pi and not the other one, right? Sorry, 2 pi. Or you do the thing that I said we're discussing last time. You swap them. That's rotating both of them by pi over 2, right? So this minus sign is observable if you arrange for an experiment that treats, say, two such spin half particles differently. So this is a line of logic. Quantum mechanics allows, well, in quantum mechanics, we model states, systems by complex vectors. The overall phase of that complex vector is meaningless unless you treat different particles differently and you could interfere them. The fact that the overall phase is meaningless, it allows you to represent your trivial operation, like going around by 2 pi by phase multiplying the kets. This is how quantum mechanics allows for spinners, right? Quantum mechanics says that overall minus sign doesn't change your physics. And then in the world, we want to represent rotation by 2 pi, which shouldn't change anything, by an operation to the kets. And in principle, it could be a phase. Quantum mechanics allows for it. We go out there and we see all sorts of spinners. As a matter of fact, we're all made of spinners. Okay, we talked about bosons and fermions. How much of your mass is bosons and how much of it is fermions? You know? Are you mostly bosons or mostly fermions? What bosons would you be? You know? What's most of your mass, actually? What's the most of the mass of human being? No, but like in terms of molecules. Water. Water and carbon, right? Well, H2O and carbon. That's most of what we are, right? So water, you know, hydrogen, oxygen. So so let's pick hydrogen, or doesn't matter, oxygen. What's most of the mass of it? The center, right? Protons and neutrons, right? So protons and neutrons, what are they made of? Are they fermions or bosons, actually? They're fermions. They're actually composite particles. So they're made out of quarks, which are also fermions. They're spin half, right? But they are held together by a bunch of bosons called gluons. And turns out that most of the mass of protons and neutrons are actually those gluons. So most of your mass is that strong particle called gluons that, that's why you weigh so much. When you do exercise, you get rid of some of those gluons. All right. All right. Okay, so now you might wonder, how is it? So what does it mean when I say this -1 doesn't have any consequences if you apply to all the particles? For one thing, it should not change the expectation value of anything. Is that clear why? Because expectation value have a ket and a bra. So 2 -1s cancel. As a matter of fact, it could have been a phase. Because e to the power of I5 would be for the ket. The bra would have e to minus I5 that would cancel. None of the expectation values would care, as they shouldn't. Right? This e to minus I5 is what we get for a Nobel Prize for. We give Bolchak the Nobel Prize for when we talk about the, I'm blanking, what are they called? Anions. Right. Okay. All right, here's an example. Let's say you had some ket and you were measuring Sx, the expectation value of x, spin in the x direction. Now rotate it around the z-axis by angle phi, right? How does that change? Well, let's look at the operator first, right? Now you have to use Baker-Campbell-Hausdorff. This thing is your friend. I absolutely insist you should know this. Memorize it back and forth. It's so important, so helpful. Baker-Hausdorff-Campbell tells you that if you expand this operator, it's Sx plus I phi over h bar SDSX, right? And then this nested commutator. These are called nested commutators, right? So the first one is IH bar SY. How do I calculate this? So the commutator of SZ and SX were, let me do it on the book. All right. So I'm calculating SZSX, right? That is H1 over 2, H1 over 2, right? So let me just write them here. H1 over 2, H1 over 2. Sigma Z, sigma X. What was this? This was 2I epsilon ZX Y sigma Y. Right? Let's eat one of the H bar over 2 into this so that we get H bar, this 2 and 2 cancel. IH bar epsilon ZXY SY. What is epsilon ZXY? It's 1. Yeah. All right. Then that's the commutator. You have to calculate SZ and this guy, IH bar SY, you get H bar squared over SX, and then you repeat that. You realize that, as is common with this Pauli matrices, all the even powers take one form and all the odd powers take another form. So you could resum them and you obtain the following resummation. This is something that one way or another I'll make you guys do in homework so that you get used to it. You end up with Sx operator rotated around the z-axis by angle phi becomes Sx cosine phi minus Sy sine phi, as it should be. Right? Good. Is that intuitive enough? Right? Because what you're doing is rotation around the z-axis by angle phi is a rotation in the xy plane. So this is the matrix we're acting with. I wrote it and erased it a million times. Cosine phi minus sine phi sine phi 1. All right, here's how the expectation values change. Sx, if you did this calculation for all of them, Sx goes this way, Sy goes this way, Sc goes this way. So actually, I think I have a slide with, I should move this slide. Oh, okay, never mind. So what does this mean? It means the following, that if you look at the expectation values, so if I look at the expectation value Sx, expectation value Sy, the expectation value Sc, what they've done to it is a rotation. Right? This is what I've done to it. So the rotation matrices are acting on the expectation values. Right? That's consistent with the fact that this is supposed to represent rotation. More generally, for any spin, you have this relation. Of course, that's a must. But the expectation values don't pick up that subtlety of the extra minus sign potentially for spin half. Right? So let's try to focus on that spin half thing. Are there any questions? I have to pause here. Let me say in words what this says. We had the rotations that in our classical world think of as represented by three real matrices. That's what we do to vectors. To represent this for a spin half particle, we have to represent rotations by 2x2 complex matrices, unitary matrices. Now, when we go to this Hilbert space, when we perform a measurement, often we're interested in expectation values. Even though it's a complex vector space, but the expectation values of observables are always real, right? And if you package them as a vector, in this case, because they are real, they transform like 3x3 by the action of the 3x3 real matrices. So the expectation value of Sx, Sy, Sc acts as a three-dimensional vector, a real vector, right? This is, like always, well, the way I have in mind is that this is the real three-dimensional, I should say real, well, real parameters space, and then you go to the Hilbert space, that weird algebraic stuff. You go there and come back, right? Any questions? All right, so now we're after that angle phi, angle minus one, that phase minus one. So let's apply a rotation by angle phi around the z-axis to a two-dimensional ket, alpha plus alpha minus, right? How does it change it? It will change it by e to minus phi, I phi over 2, e to the power of I phi over 2. This is something you should check. It's sort of obvious from, I already gave you the expression, just put phi equal to pi in there. So that means that after rotation, a ket, rotation by z, around z-axis by 2 pi, a ket picks up a minus sign. Good? So you have to go around, but that means that if you go around by 4 pi, 720 degrees, you get back to your initial vector. The expectation value of observables are unaffected by this because you pick a minus sign from the action of the d on the ket alpha and another minus sign from the other one, so they cancel out. This is the summary of what I've said. I just repeat myself many times so that it clicks. Good? But of course, all right, so let me take a step back. In the next few minutes, I'm going to build up towards measuring this minus one. Good. So to do that, we first are going to do a calculation we've done before, the very beginning of this course. This is just spin half particle in a magnetic field, Stern-Gerlach, spin per session. So we're going to do that again, right? And it's not a new calculation, but now you see the calculation in a different light, right? And then we're going to talk about how to see the minus one. All right, what was the calculation over there? Let's say you have an electron or any particle that has charge, electric field, charge this unit -1, whatever it is. So I put an electron as if it's an electron, right? So the Hamiltonian is going to be minus electron charge over MEC S dot B. We're exposing it to some magnetic field. You could always, if the magnetic field is in the Z direction, you could view this as just BZ, right? Omega is this. So I'm just, hopefully you remember, we had this example of magnetic field being in the Z direction. Time evolution due to exposure to magnetic field in the Z direction is just e to minus I S Z omega T over H bar. Why? Because this is minus I H T over H bar. Right? That's time evolution applied to kets. Good. So you already know that if you arrange these kets, Sx0, Sy0, Sz0, these are times, right? So I'm in the Heisenberg, I'm pretending I'm in a Heisenberg picture, right? They transform this way. Sine omega t, cosine omega t, sine omega t minus cosine omega t. So the expectation value after time 2 pi over omega come back. Because cosine and sine have periods 2 pi. Good. But if you did this to a ket alone, you'll pick up e to minus I omega 2, e to I omega 2. Well, why did I write it this way? No, I don't like this. This is bad, sorry. So let's just say your alpha 0, T naught, what was my notation? T naught equals 0 is C1, C2, so that this is C1, C2, good. So it's pretty clear that now you have to go by 4 pi over omega. You have to be exposed to the magnetic field for 4 pi over omega so that they come back. If you're exposed to it only by 2 pi over omega, even though all your expectation values come back, but your ket picks up a minus sign. Good? So how do we measure this? The main principle is interferometry. This is the good old double slit experiment. Right? All the experiments that we have, all the things we talk about, either string yellow black or double slit. So you take two beams. So this case is like, I think the experiment is done with neutrons, but it doesn't really matter. Also have particles. So we take two of them, or it could be actually one, doesn't matter. Or some beam, bunch of them, right? There are two paths that they can follow. There are two slits, and then on this side, you see some sort of an interference path. Good, you see something. Very good. So let's say if you pick a point here where they constructively interfere, you get something. Then what you're gonna do is you're gonna turn on, pick a region here, only here, and turn on some magnetic field B. Now this particle is exposed to the magnetic field for a certain amount of time. If it's moving with the speed of light, it's c over the length. Speed of light over the length, right? That's the time it's exposed to it, and during that time, it will pick up this these phases, e to minus I omega capital T over 2 and e to I omega capital over 2. And when they come back, the interference pattern has changed. So by let's say you fix the length and change the B. When B is 0, you pick a point. As you increase B, the interference patterns shift. You go from constructive all the way to destructive, right? How much is that destructive phase? If you have to go 4 pi to come back to it, two peaks would be separated by angle 4 pi, right? So after 2 pi, they actually cancel, right? But if the particle didn't have this extra minus sign, after 2 pi, you just see two peaks. So from as you change the B and how the peaks change, you deduce this phase. So let's explain that in a little bit more detail. Well, actually, it's not more detailed, but it's basically what it is. So you'll pick up, let's say when there is no magnetic field, so the time that the time that they're exposed to it is 0, then there is some cosine of theta, is the phase difference at the point. Then as you turn on the magnetic field and one of the particles is exposed to it for some time t, there are these extra phases. For these extra phases to go between two successive peaks, right? It takes 4 pi c over L, right? Not 2 pi c over L. Okay, let's pause here, ask for questions, and then I'll tell you something else. Are there any questions? L is this is the travels. So when I said that in the expansion of the unitary operated X on the Hilbert space, the generator was S or J, whatever I called it, and then there was over 1 over H bar. And I said this H bar is the same H bar of Hamiltonian. Using this time experiment, you could argue for it. It must be. Yeah, just 1 second. Similar arguments led to the fact that H bar of X in H bar that appeared in translation and momentum and time are the same, right? Because we wrote down a Hamiltonian that momentum was generating time evolution. Here we wrote down a Hamiltonian where rotations is generating time evolution. Yes. It's louder.
Is there a relationship between phase difference and frequency of that?
Say it again.
Is there any relationship between delta and B? The phase differences.
Oh no, delta is just the geometry. Delta is when you turn B off, it's whatever configuration you had in your lab, right? Delta is like the difference in half. If the particles that were prepared were synchronized in their phase and they were going the exact same length, the delta would be 0. It's just a setup of your lab. If it helps, pick a setup where you prepare a pair of particles, or it doesn't matter. Let's say coherent beam where the phase is fixed, right? They travel the same distance. This path is the same distance as this path. Then there's no delta. So just drop delta and. But you can calibrate for that. It's funny as a theorist. I think I say the word calibrate once a year. All right. Any other questions? Is that good? What is the
Difference between B0 and
when B is 0, this particle propagates all the way. Right? When B is non-zero, during this length, during this time or this length, as it goes through this, it undergoes an extra evolution, which is e to minus I omega t over 2 phases. B. There's a B in there, right? That's an extra evolution that it's like the way we do science, right? You wanna focus on that evolution in particular. So this is your sort of like, what do you call it? The one that doesn't undergo that evolution, and this is the one that does. This is your control, right? And you look at the interference between them. Right? This does not undergo that evolution. This one does. So you might, like if you're a skeptic, you could have said that, oh, I wrote some sort of, like you could try to say, oh, maybe there's some sort of complicated setup. There are all sorts of other forces, and this way of arranging it just arranges, sort of like gets rid of that. You say that, well, whatever the path is, I'm going to measure delta, some interference pattern. Now, the only thing I'm going to change is add a magnetic field here, and then the phases, the patterns change. Okay. All right. In the remaining couple of minutes, about 10 to 15 minutes, what I'm going to do is I'm gonna once again repeat a lot of these mathematical formulations that we discussed, but in a more organized way and more fundamental way, in a sense. And I want to use the terminology of groups because it's crucial. It's absolutely crucial. All right. So there won't be new physics as we go forward until the end of this lecture, but it's just repackaging of what we've said. Going back to the beginning of the previous lecture, a rotation in three-dimensional space can be characterized by three real numbers. For example, if you're rotating around some direction n by some angle phi, what are those three parameters? Phi is one of them. The other two variables tell you about the direction of n. N hat only has two real variables, right? Because the norm of it is unit length. So those are the three variables. Or you could think of Euler angles, if you remember from classical mechanics what Euler angles are. We model this using orthogonal matrices. These are matrices that satisfies this. R transpose R is equal to identity. Well, okay. I'll give you the sharp definitions at the end. Doesn't matter if my comment is a little bit imprecise. R transpose R is identity equal to R transpose. So any matrix of this form has three real parameters. Why? Because it's 3 by 3 real matrix. How many components does it have? It has 9. How many equations are there here? 6 equations. Right? So 9 minus 6, there are 3 parameters left. Good. Those are sanity checks. Of course, it forms a group. It satisfies all those things that we said. There's an identity element, which is the identity matrix 1, 1, 1. It is an element of this group, right? So the group is a set of all 3 by 3 real matrices that satisfy this relation. R transpose R is equal to R transpose equal to R, right? Identity is a model. Every element has an inverse, which in this case is just inverse of R. It has a unique inverse. Inverse of R is R transpose. And then there is multiplication that's associative. And then if you multiply 2 of these matrices, you get another such matrix. That's what a group is. A group is a bunch of abstract things, apples and bananas, where to every apple, well, first of all, there is an identity. There's an operation. You could pick an apple and banana and get some other element out of it. So 2 things go to 1. 2 fruits go to 1 fruit, right? Multiply 2 fruits is always a fruit. Every fruit has an inverse, meaning that there is a neutral fruit that you could inverse, right? So that thing is it's a group. That's what the group is. There are many translations form a group. In space, translation in time form a group, rotations form a group, boosts form a group. All of these are groups. Reflections form a group. What's the difference between reflections and rotations and translations? Reflections are discrete groups. The elements, if I'm doing reflection around a particular axis, like I reflect and reflect back is 2 elements, doing nothing and reflect. Because if you multiply them again, you get identity, right? That group is Z2, it's discrete. These groups you're talking about are continuous. That's why I could talk about infinitesimal generator. Like all of this is logical. The story of how we understood the significance of groups in physics goes back to Emmy Noether, where she realized that if you have a continuous symmetry, a continuous transformation that acts in a particular way, these are all symmetries, then it's talking about, it's related to conservation laws, blah, 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 right? This goes back to early days. So over there, we're talking about continuous. Often continuous symmetries are very, very powerful. So this is what the group is. R transpose equal to 1 tells you that the determinant of R squared is 1. Why is that? Yeah. Well, R transpose R is equal to identity. Take a determinant of both sides. This is one. What's this is determinant of R transpose times determinant of R. Determinant of R transpose is determinant of R, so determinant of R squared is 1. So there are two choices. Either +1 or -1. Good? The plus ones, what is the determinant of this? 1. Give me an example of an orthogonal matrix with determinant -1. Oh. But give me another example. This, right? Or this. So what you could do is you could think of rotations. This is not a rotation, by the way. What is this? It's sort of a reflection in all directions in space. In physics, it has a name. Center symmetry? No, not really. What would we call this? We've heard this a lot. Parity. This is parity. It's a Z2 symmetry. It's a symmetry that was just discrete symmetry that comes back to itself. Rotations can never do parity, right? So rotations are matrices that satisfy that relation, R transpose equal to R transpose R equal to identity, and on top of it, they have determinant 1. Turns out that this, in a lot of systems, is also a symmetry, but we could discuss that separately. Good? All right. So orthogonal means this relation. 3 by 3 matrices. Special means determinant of R equal to 1. Special orthogonal 3 by 3 matrices is called SO3. So SO3 are 3 by 3 are 3-dimensional representations of rotations, real representation. Good? These are those cosine phi's, sine phi's that you recognize. It's called SO3. It's a group. Everyone's with me? Now, what is the name of the group that describes the rotations of a qubit? We modeled it by 2 by 2 complex matrices that are unitary. So they satisfy UU dagger or DD dagger. I call them D, but now call them U. Is equal to D dagger D equal to identity. Okay? So now, by the same analogy, what is the determinant of U? If I take that U dagger U, this has to be 1, right? So I have determinant of U dagger of U is equal to 1. So what is the determinant of U dagger? It's determinant of U star, complex conjugate. So the whole thing is determinant of U dagger, the U norm of it is 1, which means that determinant of U could be a phase. Right? So you could have transformations that do this. Sorry, transformations that are like this are included in that, but these are not rotations. Rotations are 2 by representations of rotations acting on a spin half particle 2-dimensional Hilbert space are 2 by 2 complex matrices that have determinant 1. So these are unitary, unimodular means determinant 1, 2 by 2 matrices. That's called SU2. Good? Everyone's with me? We represent rotations, which is SO3. So SO3 is a group of rotations in the 3-dimensional vector, real vector space, right? Here, SU2 is the way we represent it in the Hilbert space. You already see some funky thing between them. We saw that there's a difference between the two. What was it? SU2 is a double cover of SO3. When you apply a rotation by 2 pi, SO3 matrices come back to identity. SU2 comes back to minus identity, right? If you go again by 2 pi, SU2 comes back to identity. So SU2 is like going or doing rotations in the spinners where you do rotations, but after 2 pi, you come back to minus identity, you do rotations again, and you come back to identity after 4 pi. It's a double cover of it. An analogy is, this is an, if you know topology, it's very precise. If I have a circle, it's a group. Rotations in 1 dimension, right? I go around by 2 pi and come back with this. Something that goes around by 4 pi comes back where it is. A double cover of a circle. Let me just try to draw it. You go around by 2 pi, you do not come back where you started. You have to go around by another. You go around by 2 pi, you do not come back where you started. So poorly. Yeah, you have to go around by 4 pi, and then this is this. Right? So you go around twice and then attach them. Think of a coil, right? You go around, you go attach them, or a chain. Or you go around, you're locking your bike, it's gonna get stolen anyway. You go around twice and then you put them together. Right? It's called a double cover. So you learn that SU2 is a double cover of SO3. SO3s are rotations in 3 dimensions. Spin half particles are the ones that as you go around by 2 pi, you pick a minus sign. So we model them by the group SU2. Good? All right, I just have one last slide. So the same way that we talked about we're going to talk about Euler angles again. There were 3 real parameters in SO3. There are also 3 real parameters for SU2. Why? Well, take a 2 by 2 complex matrix. The fact that it has to be unitary tells me that if A and B are complex numbers, right? So you start with how many variables? You start with 4 complex numbers, that's 8 variables. The fact that it's a unitary tells you that A, on the diagonal, you have A, the second one is A star, and then you have to have this minus B star over there. That means how many parameters you have? You're left with 2 complex variables. That's 4 real parameters. And then the fact that determining that U is 1 tells you that A squared plus B squared has to be 1. That's 3 real parameters. Sanity check, right? Rotations have 3 real parameters. Okay, let me say this. The set of all matrices that satisfy this relation form a group. It's called the orthogonal group. These are n by n matrices, real matrices, right? This is called ON. If on top of this, if you also have the determinant of R is equal to 1, these matrices also form a group called SON. If you have matrices, so this is one line. If you have matrices that satisfy this unitarity relation, this form a group. It's called UN. If these are n by n matrices, right? Complex matrices, of course. And if you have determinant U on top of it equal 1, this is called SUN. SUN is a subgroup of UN. SON is a subgroup of 1. What does ON have on top of SON? Sorry. What does ON have? What does ON have on top of SON? What is this group physically? If you say O3, how do you describe O3 physically? This rotations, and parity. Right? This is all rotations. What you have in here that you don't have here is just parity. So if you're allowed, if instead of operation you're allowed is rotate, parity, all of that, that forms this group. Good. What is the extra operation here from SUN to UN? Multiplying the kets by a phase, all kets by a phase. Right? That's an arbitrary net that we wanted to discard, say, is pronounce on physics for now. Right? All right. Thank you so very much. Are there any questions? Let me just repeat that November, oh my God, 12 and 26, did I get it right? We're going to be on Zoom. Thank you so much, guys. There will be a new homework posted. If you have complaints about